And I also realized that I only have 2 lectures, okay? So I don't know how to resolve that, okay? So I'm just going to plow ahead, and at some point I'm just going to stop and my lectures are over, okay? I don't know any better way to do this. So what I want to do today, actually I want to start to go from singleton to linear logic. In other words, generalize away from what we had so far so we can write richer programs. But I also already promised that I'm going to show you how to do Turing machines, and it's actually pretty cool, so I do want to show you that as well. When you come to linear logic, what we'll see is that a lot of the things we already discussed, they still hold exactly the way I told them to you, except you have more, you can express additional things. And so we'll just figure out what those additional things are. Okay. So I like to program, and actually I have an implementation of the singleton logic that I told you about, which has lots of bells and whistles and lots of additional features. We spent a lot of time and effort actually implementing this, but we never actually gave it to anyone, okay? So if you're actually interested in playing with that, maybe you can send me an email and you can download it. There's actually like a grammar in there, okay? So you can actually, it's pretty close to what I do on the board, right? The board doesn't get type checked, but nevertheless. And you can execute the code, it'll run concurrently. You can see the output of your programs. And then there's like 3 additional things that I probably don't have time to talk about. So one is you can track exactly how long your program will run. So there's a temporal extension of this session type system. And the second is you can track exactly how much work your program will perform, how many operations it will do. So one is a sequential complexity of your program, the other one is parallel complexity of your program. And then in order to do that, there is a version of dependent types in there. So they can, for example, you can say that, well, depending on the length of the queue, if the queue is length n, it'll take 2n operations to add something to the queue, things of that nature. So you need to track things like length of queue and so on. So we have some arithmetic in there and some decision procedures and so on. But I decided that it takes too much time to actually like demo it. But I'm willing to distribute it if people are interested. So anyway, so I'm just going to use the board, okay? And you guys have to be the type checkers, right? Okay, so I want to implement a counter. So I want to implement some things on natural numbers, okay, in binary form. So remember the type of binary numbers is an internal choice between a bit 0, which gives you another binary number, or a bit 1, and then you continue to be a binary number, or it's the end, and then we'll just have some type alpha. Actually, in the implementation, we have an additional type 1, and I'll explain that towards the end of the lecture. So it's slightly different than what I'm showing you on the board, but okay. Okay, so now an interesting question is, so I'm getting a stream of bits which I assume will terminate with E, okay, end of stream. And I want to output on the other side of my thing the successor of the number that I'm getting. So that's my programming exercise now. So the type will be something like this. So the successor process produces a binary number, so a bit string, given a binary number on the left. And this is, remember, this is an internal choice, so the information flows this way, from left to right. Okay? All right, so now let's just start. Let's just go ahead and do this. So successor equals. Okay, so what does this program actually have to do? It has to read, yeah. So do we read from the left or from the right? Left, because this is an internal choice, right? And so it's going to send us a bit. So we do a case left, and we could receive bit 0. Or we could receive bit 1, or we could receive an end of number thing, which represents 0. Okay, so if we receive bit 0, what do we output on the other side? So in this representation, this is a little endian representation, so we get the least significant bit first, okay, rather than the most significant, yeah? Yeah, okay, so we output 1 because incrementing any number, the least bit is 0, gives you 1, right? So we we send bit 1 to the right, and then what do we do with the rest of the number? Yeah, so the last, we keep all the other bits, right? Because incrementing the binary number is taken care of by changing this bit 0 to bit 1. So we just forward, right? Which is the... Now there's another choice I could do here. I could call a copy function, or copy process. And what the copy process does, it takes every bit from the input and takes it to the output, right? So I have a choice here. But I don't want to write a copy function right now, so I'll just forward. Has the same effect in the end, right? Except that the copy process is slower, right? Because it takes it bit by bit. And the forward just gets rid of and connects the channels and just gets out of the way and terminates. Okay. Okay, if I get bit 1, what do I have to do? So this the least significant bit is 1, and I'm trying to increment my number. I output bit 0. Okay. I flip that to 0. And now how do I implement the carry bit? Yeah, I call myself recursively with the successor because it takes the successor of the rest, so I just do that. Okay, does that make sense? Now I increment the number that comes after that. Okay. If I see E for the end of input, what do I want to output? The 1. Okay, so I send the bit 1 to the right. Okay, and then I have to send E, exactly. And then I forward, because now both sides of the process will have type alpha, and I can forward between them. Okay, the program makes sense to everyone? Okay. So I went so far, actually, like I said, if I share the implementation, the most complicated code I wrote is one that takes a binary number and returns essentially true or false if it's divisible by 3. Okay. I just wanted to see if it's doable. Okay. And it's actually, it was pretty challenging. Okay, because you have to divisibility check by 3 on these binary numbers. You have to take some kind of a sum. You have to add the digits. And then you have to make sure that they don't overflow and things like that. But I did get it to work. Okay, it's a pretty nice, stupid exercise. Okay, but a fun thing to do. Okay, but what I want to do is I want to combine now something that uses external choice as well. So this is kind of like stream programming, kind of functional programming style. Next thing I want to do is more like an object-oriented programming style. Okay, so I want to have a type of a counter. It's an external choice, and the environment can say, okay, well, increment the counter and behave again like a counter. And maybe the environment can say reset the counter to 0. And the environment could say, well, give me the value, and then it turns into a binary number. Okay? Okay, so now the implementation is going to be something like this. So an implementation of a counter is going to offer the counter service to the right, and it's going to have the binary number to the left, and this binary number represents, well, sort of the local storage of the number that the counter currently has. Okay. And here is where I receive requests, an increment request, a reset request, or the request to actually give up the value. Does it make sense, spec-wise? Do we know what we have to do? Okay. All right, so how do we implement the counter? Okay, so there's two choices. We could either try to read a bit from here, because that's an internal choice, or we can try to read a command from over here, right? A message over here, in the sense of object-oriented programming messages, right? We're getting a message to increment your internal state, reset your internal state, or return the value, right? Do we want to read a bit from over here? Probably not, because what would we do with it, right? not much to do with it. So we read a command, so we do a case write. Okay, and there are three possible commands we get: an increment, a reset, or a value. Okay, so now we have to see what we do in each case. All right, so if you get an increment command, okay, what we want to do intuitively is this number here, which we're holding on the left, we want to increment that and then recurse, right? How do we get to increment this number? How do we do that? Yeah? We can call successor, but how do we call something here? How do we call? If we just call successor like that, that will be the wrong type, right? Because successor, it takes a binary number to a binary number. If I do successor, counter, so we can't do that. Yeah? No, I don't think so, because the binary number here, I can't call myself. I can't pass a value to myself, so I don't really know how to do that. Yeah? Yeah. Okay. So we call successor by spawning a new process, which will do that, right? And then we call ourselves recursively. And so let's see, what would be the type of this composition here at this interface between this successor and this counter? Bin, right? And on the left-hand side, the successor will be a binary number, which is good because that's what we have here. And on the right-hand side, this will have type counter, which is good because that's what we still have to present to the outside. So everything type checks here, okay? So calling something actually usually corresponds to spawning a new process, making sure that the interface works out, okay? Now, there's a nice piece of concurrency here, which is that because this is a concurrent spawn here, this successor can now operate in parallel with we getting other commands, right? So you don't actually have to compute the full increment here, okay? If you need some information from here, for example, the first bit might be available almost immediately. So these things actually get some concurrency here by doing the increment concurrently with getting more commands on the right-hand side. Okay. Now let's say we're supposed to be able to, supposed to have to do a reset of the counter back down to 0. How do we do that? Yeah?
Write B0 and then forward, and then compose with counter.
Okay, write B0. So we cannot say r.b0 because to the right, our interface on reset is still counter.
Right.
So we can send B0 to the right.
But compose that with counter.
Ah, okay.
As in, and then so sequence with forward.
Okay. So we sequence that with forward and compose with counter. Okay, so this will not pass the type checker. Okay, you guys are the type checkers, why not? Well, let's first look at the interface type. What would be the interface type here? Bin, okay. What would be the type here? Counter. What would be the type here? Bin. Okay, so it looks like a type check, but it doesn't. What did we overlook? Okay, so after we send B0, okay, so then that forward will connect these two. So I take it back, it type checks, okay. But does it reset the counter? Nope. What does it actually do? It doubles the counter. Okay, because putting a B0 in, as a new least digit and then forwarding means you're multiplying your number by 2. Okay, so the type checker would be happy. But when you actually run it, the reset doesn't have the effect that you actually would expect. Okay, so that's very useful exercise. Okay, so bonus for getting it type correct. But how do we actually do the reset? Yeah?
Could you write a function similar to suck, but it's just zeros at top, and then do the same thing that you did in the increment case, but with the zero function?
Okay, so we need some kind of delete, let's say, that deletes the number. Okay, what type do we want to give it? Bin to bin. Okay, and delete is, how do we define it?
You could do a case L.
So we want to do a case left because we want to see what bit's there so we can actually like consume it. Could be 0, or it could be B1, or it could be B0. Yeah, we just continue deleting, right? Okay, B1, we continue deleting. All right, and if we see E, just forward. Okay, so after we see E, according to the type over here, the type on the left-hand side will be alpha. So we can't actually forward because on the right-hand side you still have to produce a number.
So you write a 0 and then
Yeah, but how do we write a 0?
R.E.
R dot E, and then we forward. Okay? All right, so then we use that here to delete that in parallel with the counter, and the types work out. Okay, now that has less parallelism because this, if you have a number n, this takes log n bits you have to consume, and meanwhile delete is looping here, not producing any output until it finally says now it's going to be 0, right? So it has less parallelism than this case, right? Because here we only have to produce 1 bit in order to be able to continue to work, and here we have to work through all the bits to reset it down to 0. Make sense? Okay? And now if we're supposed to produce a value, okay, how do we do that? So let's see, after value, we're supposed to be of type bin. How do we do that?
Could you just say forward?
Yeah, we just forward, that's it. So that was the easiest case. Okay? The counter process terminates and we put the value. Of course, when we read the value like this, the counter is gone, right? So this is one of the problems with linear programming, right? Any data structure that you use in any way, right, disappears under your hands. It just disintegrates, right? Because you're actually using it when you're using it while you're consuming it as part of you doing it. So the counter is gone. So if you want another counter, you have to start over again. But there's other techniques that will come when we come to full linear logic to actually make sure that we can do some reuse of data structures. Okay, so here's our counter. We need to write the delete function. There's our successor. Okay, just some more programming exercise. Okay, so let's do Turing machines. Okay. Because it's actually interesting to see that in this very simple language, you already have the expressive power of Turing machines. Okay. All right. So how are we going to actually do this? Okay, so a Turing machine has a tape, okay, which is like two-way infinite. And we have a current cell, and there's a read-write head that points at the current cell, and we have some symbol in here, maybe like a symbol A. And what we can do is we can read the symbol of that at the current position where the tape head is. And based on the transition function, which is a finite control of the machine, we can write some new symbol here, potentially writing A back if we change it, or write a symbol here and move to the left or move to the right. Okay, very simple. So the transition function is something like this. So we say transition function from a state Q, reading the symbol A. Okay, we have to return three things. First thing is the symbol we have to write. Maybe you have to write the symbol B. And then some indication, okay, one of two things, move to the left or move to the right. And then the third thing is the new state. Let's call it P. So this is a new state. Okay, so this is the symbol we write onto the current cell, and this is the move. Okay, so that's what we want to implement, right? I'm not going to worry too much about like whether the Turing machine accepts or not accepts and final state of it, just the computation itself, okay? All right, so now how do we actually represent this? Okay, so what we want is that, maybe writing over here, that the current cell is actually executing some process Q. So every state is implemented as a process with the same name. Well, let me call it Q hat, okay? Because I'm going to have to work with this in a second, okay? And that the cells which are to the left, A minus 1, A minus 2, and this is A plus 1, A2, and so on, that these are messages. These messages here have to flow in this direction, and these messages have to flow in this direction. And they have to flow in this direction so that potentially this Q can see either of them, okay? Okay, so that's the basic idea, right? The tape is actually represented as a whole sequence of processes, and these processes send the messages kind of to the middle. And then we have to see that we can represent the transition of the configuration as a transition, as a operation of these process definitions here, where they are one different process for every possible state that the machine is in, okay? All right, so before we do that, we have to worry about the types, right? This all has to be statically typed. So based on this picture, if this is a process running and these are messages coming in, what should be the type of Q hat? Well, right, so we get messages from the left, okay? So on the left-hand side, we're going to have some internal choice of something, right? It has to be an internal choice because we want to be able to read the messages from the tape, so they have to flow that way. And what do we have on the right? Well, it has to be an external choice because the messages flow this way, right? We have to be able to read them to the right as well. So it's a weird thing, but we have to be able to read and write from both the left and the right. And so we have an internal choice here, an external choice here. Okay. So what does the internal and external choice looks like? So on the left-hand side, we have tape, internal choice, and it could be the symbol A, and then it's again behaves like a tape, right? Because the next thing after that is again a tape. Because once we have processed this one, it just looks like a tape. Or it could be a symbol B, and then it behaves again like a tape. So for each element of our alphabet, okay, there has to be a case here. That's a finite number of cases, so that's actually okay. Let me just do 2, so I don't have to write too many dots here. Okay, but this has to be, does it have to be finite? Well, if I actually want to run a machine, it better be finite. If I don't care about running the machine, I don't care. Well, maybe we don't care, okay? So it's just an infinite stream of messages coming, okay? Okay, so then what do we have on the other side? Okay, so we have the mirror image of that, which a student of mine decided to call EPAT, okay? All right, and it's an external choice between A, and then this still behaves like an EPAT, or B, and it behaves like an EPAT. Okay? Does that make sense so far? So we have messages A and B coming in, symbols A and B, and in the same way. Okay, so now, when we want to implement the tape, the state Q, what is the type of every Q? Well, every state Q has a tape on the left and an EPAT on the right. right? Because the state is in the middle. Okay, so at this point we have another branching factor how to actually do this. I actually decided to take every state in the machine and implement it as two different processes. One that looks to the left and one that looks to the right. And the problem is that this exact picture is hard to represent because it's hard to say what it means that the tape head is exactly on A. Because somehow in the configuration it has to be somewhere in between. Okay? So we could just define we're always looking to the right. So this is the thing that we read. But it turns out to be easier if you say, well, they could be looking to the left and this is what we're looking at. Or we could be looking to the right and this is what we're looking at. Right? So there's two possibilities. Okay. We actually have two possible states here. One Q looking to the left and another one Q looking to the right. Okay. Hopefully they achieve both correct transformations of our configurations. Okay. All right. So
what notation did you use in front and before and after the Q? I can't quite read the little letter.
oh, it's a little triangle that points in one way or the other.
Okay.
Okay. So indicating that the direction we're looking at. Okay, so maybe, okay, I don't think we need this anymore, so I have to write it here. Okay, so the question is how do we implement these little processes based on the transition function, okay? So let's take a particular case. So the transition function from Q and A is to write B, go to the left, and go to state P. Okay, so that's our transition function. And now I have to translate this to a corresponding piece of code, actually two pieces of code, right? One for this function, one for this process, one for this process. Okay? All right, so let's look at the left-looking case first. Okay, so what's the situation? We have a tape here, and then we have A, okay, which is a message passed in our direction. We have Q, which is looking to the left for the next thing to do. And then we have other things over here, the rest of the tape. And what do we want the configuration to look like after the step? Okay, so this tape is not affected. So what would you want this to look like? So presumably all the ... stays the same.
Can you change that?
Oh. Okay, so the question is, we're still going to have two cells here, but what are we going to put in these things? Yeah?
So Q to the left?
P to the left because we transition to state P. Yeah?
And then the A should be replaced with a B, and it now looks to the left.
And B has to look to the left. Okay, does that make sense to everyone? Okay, so because we're supposed to move the head to the left, this looks to the left at the next symbol that comes after. Yes? And we have to write B. Well, we're writing B in that cell. That's in the right, because these cells here are now next to that. So the tape is still correctly represented after writing B into the current cell. Okay? All right, so now we need to write the piece of program for this Q. So somewhere we have a definition that says, let me write it over here. Okay, so left-looking Q. Okay, it's going to start with the case left, correct? Because it's left-looking, so we're looking at the symbol coming from the left. And the thing we're concerned about is, what if it sees an A, right? Because that's the picture we drew there, and this is the transition we're looking at. Okay. So we want that the configuration takes a step from this to this, okay? if this is what our transition function says. So now how do you write the code to accomplish that? So this bar here for the machine actually can be a parallel composition, okay? Right? So we have a parallel composition of two things. To the left, we're just calling P looking to the left and spawn that process or continue with that, right? Okay? Now, when we do the case left, we actually consume the A, right? Because we read the input, so it's no longer on the tape. So this A is gone, and we have transformed this to B. So how do we have transformed this to P? So how do we get B to appear? We put it here, right? What is the process that sends a B to the right? Oh, sorry, B to left. Okay, we send to the left the symbol B, and then we forward. Okay, does that make sense? So the process Q that's sitting here, right, that's this one. It reads the symbol A coming from the left. It becomes the P. It makes sure that it leaves the B behind. And the B has to be going to the left. Okay? Okay, so that's the case for A. And then the case for B. We have to look at the transition function for Q when it sees a B. Okay? Okay. So another interesting part is what happens when we're actually looking to the right. So let's actually also put this. Okay, so then the picture starting looks like this. We have Q looking to the right, and it sees an A. Okay. What should it look like afterwards? If this is what our transition function says. So presumably things happen in the middle here. So what should be here? If you put B here, then what should be in here? P looking to the left or looking to the right? Okay, if you have P looking to the left, then the problem is P is now going to consume the B. So it didn't really move to the left, right? Now it's looking at the B that it just wrote. You see that this doesn't quite work? B is good, but this thing doesn't work because it looks at the B now. Okay? So how do we fix that? Yeah?
B looking to the left. The A and then P looking to the left.
Oh, well, A is gone. We're writing B. Right? So this A is consumed. So we have P to the looking to the left and then B. Does that make sense? Okay, and this A, by the way, was moving to the right, and this B also is moving to the right because it's to the right of the head. So by switching it from looking to the right to looking to the left, we're actually kind of moving it to the left because now it looks at the next cell here. Previously, it sort of looked at that, and now it looks at this one here. You have to leave B behind. Okay, makes sense? Okay, so in the part of the definition for Q, for the version of Q when it's looking to the right, we have to do a case right because that's where we expect the next symbol. If you see an A, okay, then we want to achieve this situation. So we also have P looking to the left. And we have a B sending to the left. And then for other symbols, we do other things. Okay, so the code here actually on the right looks the same, even though it starts with a case right, unless we made a mistake somewhere.
Why can't you do a symmetrical version of the one for the, like, why can't you just have B moving to the right and then P moving to the right as well?
This P looking to the right?
Yeah, but so swap the order. that,
So I mean P looking to the right here,
yeah,
but then it would be looking at the B.
but then at P, that,
Okay, so A goes to, so exactly what do you want me to write?
B going to the right,
B going to the right, okay.
and then P going to the right.
P going to the right. Oh. Okay, so that would actually mean that from the step before to the step after, the machine has to make a transition to the right. So that contradicts the idea that we have to move to the left after we read the current cell. So what you have just shown here is the one, if we read B and then we go to the right and be in state B, then this is what has to happen. Okay? So there's really 4 cases, depending on whether we look left or look right and whether we have to move left and right. So we have 3 of them up on the board now. Okay? Does that encoding make sense? Okay, and then you have to do some, okay, so a nice thing about this encoding, by the way, at least so far, is that every step of the machine is exactly one step of communication, because exactly one receiving of a symbol, then moving on. So not only is it the case that we simulate the machine, but we simulate it actually step by step. Okay. Then if you want the tape to be like finite and have some end markers, you have to slightly complicate the code, but it's not very much. So since I have a lot of stuff I want to talk about, I'm going to skip that part. Okay? So you can imagine what that might be, but it's not all that complicated. So the encoding is actually very simple, right? So we have 4 possibilities to consider. We're looking at how the transition function looks, and then we encode it in the implementation of each state. Okay. And the key thing that we need to be able to do is we need to be able to spawn these new processes here that actually kind of accumulate things on the left or on the right of the process as it continues, okay? And that kind of requires, I think, I'm not actually 100% sure about this, but I think it requires this being able to have both internal and external choice, okay? Okay, so that's how we can do a Turing machine, and then with a little more complication, we can build what we call linear communicating machines. We have multiple heads that can all run in parallel and look at the tape and essentially communicate messages between them. The only thing you need to make sure is that the interface between these different states is correct, so that if the state to your right is going to try to send you something, that you're not actually trying to send something in the opposite direction, and so on. So that type checking takes care of all of that. Okay. So it's kind of a concurrent version of a Turing machine, if you will. Okay. Okay. Turing machines? Okay. So now I want to move on, unless there's a question here. People are still looking very intently at the board. Yeah. Yeah. Mm-hmm. It's what?
It's going to be waiting if the message in the message queue.
Yeah. Mm-hmm. Right. So this is waiting for here as a cell, and the state will move around, and eventually, if it comes back and happens to be looked to the right, then this message is being consumed. So it's just going to sit there, just like the tape on the Turing machine, not doing anything until the tape head comes there and looks at it and consumes it. So in this current version, right, there's only in every configuration, there's exactly one of these left-looking or right-looking states, and everything else is just these messages that are pointing inwards. But they can't do anything, because they have to, in order to actually communicate, they have to have a process that. Yeah.
So this programming language that we have now was sort of spawned from the sequent calculus.
Yeah.
Now there's not really like any sort of notion of like entailment, like the symbol doesn't really mean that anymore, like in the language or in the programming language. So I was just wondering, like, do we get any benefits out of this programming language because it came from a logic like that, or was was it sort of just like an inspiration / way of generating a programming language, and now it's like totally separate?
Okay, so when did we give up the logical reading of the entail statement, right? It happened exactly at the point when I said we introduced recursive type. Until then, there was a complete coincidence between the logic and the kind of things you can express. But it just wasn't enough, right? We need to have recursion to be able to say like a stream of bits or the tapes and so on, right? But in proof theory and logic, there's also a study of something called circular proofs, okay? Circular proofs go along with inductive and co-inductive, or least or greatest fixed points on types, okay? So you can recover the logical meaning of all of that if you want, okay? By studying under which circumstances these types should be least or greatest fixed points, and then checking that the functions in the middle actually respect that interpretation, okay? Or the processes in the middle, okay? And one of my students, Farzaneh, who is here, where is she? Back there, second to the last row, that's what she's studying, okay? So we actually have a criteria to decide. You have to declare whether you want these types to be inductive or co-inductive, or least or greatest fixed points. And then we actually have with a piece of code that you can actually download, we have a decision procedure that decides if this process actually respects the least and greatest fixed point definitions, okay? And then you get some stronger guarantees about the way your program operates, and you still get a connection to the logic, okay? But the logic of circular proofs is a little bit weird because, just like Alexandra said yesterday, normally in logic the inference rules are there to establish something is definitely true, because when you work your way up, you stop, okay, that's it. When you allow circular proofs, okay, it works differently. A circular proof has kind of this idea that you're daring the reader to refute you, okay? Try to find a counterexample. And the circular proof is valid if it's totally impossible for the person who reads the proof to find a counterexample. So constructively or intuitionistically, those aren't really the same, right? The absence of a counterexample is not the same as having definitive evidence for the truth of something. But nevertheless, it's a valid concept, and you get some interesting concepts out of there. Now, it turns out that this Turing machine, okay, unfortunately does not satisfy this criteria, okay? And that's because a certain property that you would need turns out to be undecidable, so, okay, we're actually stuck, because you can't tell if the encoding of a given Turing machine will halt on all inputs, and therefore you can't tell whether it's potentially a valid program. So let me talk about the properties that we want to hold, even though I'm not going to actually prove them. But let me talk about the properties we want to hold for this language, okay? Because I might prove them later on for the more general language, or at least sketch how that works. But I think it's very important to remind ourselves what we're actually going for. Okay. So the first theorem is preservation. Okay, it says the following. If you have a process or configuration that looks like this, so if this is typed and P makes a transition to Q, then the interface of Q is preserved, okay? So the reason that this is non-trivial is that, of course, internally, the types of the interface between processes that communicate changes, right? So the types of every channel continuously evolves. When you send a message, the type changes to be the continuation type of that, okay? But on the outside, the type does not change. So if it's plugged in with something else, they will not have a wrong idea about how you want to communicate. So that's the preservation theorem. And I already sketched to you kind of how you prove that, okay? You look at the possible transitions, then you do an inversion on the way this was typed, and then from that you can like reconstruct the typing of Q after the transition, okay? Okay, now the more interesting theorem here is progress. So if you have a well-typed process, okay, so by the way, this is just like in a functional language. There's nothing special about this. preservation, I mean, it's special only because types of the interface change, which you usually don't see in a functional language, but otherwise it's the same theorem. The progress theorem is quite different, okay? So in a functional language, the progress theorem usually says if you have a well-typed program, either it's a value, okay, or it can take a step. Now here we don't have a notion of a value, so we can't say the same thing. But we can say, so either, okay, so that's the first possibility, we can take a step. All right, so that's the easy part, right? We can take a step, we can take a step. Okay, so what's the second possibility? So the second possibility is that we cannot take a step, okay? But what do we actually want to guarantee? What we really want to guarantee, we never get into a situation, well, in a functional language, we want to guarantee the following thing. If somebody applies, for example, a first projection, it won't apply that to a function. That won't make sense. It won't try to apply a number to an argument, because it has to be a function applied to an argument. Right? So well-timed programs do not go wrong. So what we want to prevent here is any situation where two processes, the one tries to send a message, the other one tries to send a message, they're next to each other. It doesn't make any sense for that. That should be prevented, okay? So what is the analog of not being able to step or not being able to be a value, okay? So basically we're trying to characterize under which circumstances is it impossible to take a step, right? We try to write out explicitly what that means. So can anybody think of circumstances where we cannot take a step? Yeah?
It's already a value?
Yeah, but we don't have a notion of value. These are all just processes, right? So, yeah?
Wasn't forwarding?
Okay, good. P is forwarding, okay? So basically a computation has finished, and the only reason we can't take a step because this cannot cancel some other cut because there's no cut left, okay? Okay, but that's not really all the possibilities. There's a possibility.
What you just send message from one side.
Yes, we're trying to communicate either this whole process P tries to communicate to the left here or to the right here. And then it can't proceed because it needs to have a matching process to communicate with, right? Because the semantics is synchronous. Okay, so three possibilities that communicates to the left or right. Okay. And then it's perfectly legitimate to stop, right? Because you can't continue unless you can synchronize with another process, but there's none here, right? This is the endpoint. And similarly here, if you try to communicate here to the right on C, there's no process here, so you cannot communicate, so you have to stop at that point. Now, these two cases here, the first one and the third one, are not exclusive. So it's possible that you try to communicate on the left, but you can make an internal transition here, like in the middle. When you say in a functional language something's either a value or it can take a step, those are two exclusive things, right? If it's a value, it can't take a step. If you can take a step, it's not a value. But here, it's possible to be able to communicate to the left, but because of concurrency, you might also be able to take an internal step. Okay, so the situation here is more complicated. But you can actually go ahead and characterize more precisely the things that try to communicate to the outside and can internally take a step. But I don't really want to go further in that direction. But so this means it cannot be stuck because internally two things don't match, right? You have to be able to tell at the outside that you're actually trying to communicate. Does it make sense as a progress statement? Okay. Now, if we apply Farzaneh's criteria for inductive, co-inductive types, or least and greatest fixed points, and the program satisfying it, then we get a stronger statement that says basically progress is this is true, okay? And you will reach one of these two steps after one of these two situations after a finite number of steps. And in general, this is not true. Because, for example, a Turing machine might go forever and never try to communicate with the outside, okay? But if you apply an additional criteria, then we can make sure that our process will eventually try to communicate here or communicate here. Okay. So what will happen later on in the intuitionistic case, in the more general case where we have multiple, and so we can then say a process that has nothing on the left and just something on the right, that process will eventually communicate on the right, if it follows the criteria. So that guarantees that after a finite number of steps, we'll be able to get out a value. So it's a very strong statement, but not really quite here. Okay. Without a proof, but this is what we can prove about this language. Okay, makes sense? Questions about it? Yeah?
Question, is it possible to communicate to left right without stepping?
What do you mean by that?
If you communicate, you have to send or receive, right?
Yeah.
So I would assume that means stepping because I have to make a choice or to send something.
No, communication you block. When you do a case right, you actually block at that point. So you don't actually step.
It's a global property. Something will happen that matches what I'm waiting at.
Yeah. Yeah, it's a global property that eventually you will try to communicate the left or the right, but you will be blocked doing that. Because in this configuration, there's no partner here, there's no partner here.
So that's treated as a separate thing from the internal stepping upon receiving.
Right. The internal steps can take place, so that's always this, right? So a lot of internal communication can take place, even while we're trying to communicate here, because things can happen concurrently, okay? But one of the leftmost process in this, if it's a parallel composition, will be blocked and can't do anything until we compose it here. Yeah, so the way I usually think about this is not in this case, but in general, what you'd like to say something, you have something that doesn't depend on anything else, and you have a process that tries to communicate, that we have an interface to. This is something like a library we can call, okay? And then this theorem will basically say that if we're hooked up with this library, either the library is still working, or it's done. Actually, forward cannot happen because that's empty, or it's trying to communicate, so it will deliver a value back to us. Okay. Other questions? Okay, so let's start now. Actually, how long do I have? I kind of lost track of time. Okay, good. So, and we'll move on and sort of try to remove some of the limitations that we have worked with. The first limitation, maybe the most important one, is that we only have exactly a single assumption, okay? So let's say we relax that, and let's say we allow multiple assumptions. So now we should be able to do like a merge function, right? A merge process, right? We do processing, merge them. But the problem is, how do we actually, so the nice thing about this language is, communicate to the left and to the right, that's all we can do. And so somehow the nice thing is that we're so limited in what we can do. But now let's think about merging two streams. So we just put two things, we don't change our type system yet, but we just allow two things on the left. So we would have a stream of bits, and we would have another stream of bits, and we would like to write merge, and produce one stream of bits on the right. Okay, that's what we'd like to do. So how does merge actually start? So there's merge, okay, and I'm going to leave some room here, okay. So the first thing you want to do is case on this one, because if we want to read that bit, then we want the output over here, and then we want to do a bit from here and output that and so on, right, alternate. But now I need to distinguish between reading a bit from here and a reading bit from here. So I cannot just say case left, because there are two things on the left, so it doesn't work anymore like that. Okay? So what I now have to do, as soon as I have more than one assumption, I have to label these, and I label them with names of channels. So I say, I have a channel X here, and I have a channel Y here, and I have a channel Z over here. Okay, and then I use, perhaps not a very inspired choice, but I use double colon there. Okay, because the colon is used up for the typing of channels. Okay, so read this is I'm connected with two processes on the left, one along channel X, one along channel Y, and I'm connected with a client on the right along channel Z. Okay, okay on this? So these variables in a functional language we're used to denoting values or computations in Haskell. Here they represent channels along which we can communicate. It's a difference between natural adduction and the sequence calculus. Okay. All right. So now what we do is we do a case, but we not do a case left. We do a case on what's on the channel X. Make sense? So rather than saying left, we actually put the name of the channel there. Okay. And then to say, well, we could receive a bit 0, or we could receive a bit 1. Okay? Now, this is a definition up here, but in here we still need to bind these variables. So the way we do this is we notate it like this. Again, not a potentially very inspired choice, okay? So if you think of a function, it depends on two arguments, okay? But there's one more thing. In a function, you return a value. Here you don't return a value, but you communicate along a channel that actually sits to the right here. Okay, so we give the name of that. So that this reference to X refers to this X over here. Okay. Okay, after we see B0, yeah?
What is the reason that you're writing it from right to left?
Okay, so if I omit this arrow, which I can do because you don't have an implementation anyway, it's like a function call that returns something which we name. So this like binds Z. Okay, so when you actually use this notation, it's quite reasonable. If I put the thing over there on the right-hand side, it's too distant. It's very hard to see what's going on. Okay, so we tried all different permutations. At some point, you have to turn something around, and we decided this one. Okay. Okay. So if we read B0, what do we want to do at this point? We write it to Z. How do we do that? Well, we send it along channel Z, the bit B0. Okay? So rather than saying right or left, we again put the name of a channel here. And this channel just happens to be here, so it's on the right. Okay? And after that, what do we do then? Yeah, now we just flip the role of these, and now Z is implemented by merge of Y and X. Okay, we just flip those things. We're still implementing the same Z, so we're still talking along the same channel, but we give Y and X on the other order. If we see B1, we write B1, and then we flip the role of these two channels. Okay? Makes sense as a piece of code? Okay. So really, the main thing we have to do to adapt to this world of multiple assumptions, the crazy world out there, okay, is to label the assumptions with channels. And then whenever we communicate, just rather than saying left or right, we name the channel along which you communicate. That's all. We just have to get used to doing that. Okay? Okay? Yeah?
Since everything has names, does it matter what's on the left and what's on the right now? Or could we just have like everything on the left?
Okay, excellent question. So if it's an internal choice, on the left it will send you something, you do case over it. It's an internal choice, you have to send it to the right. So the position still matters because in one case, if D is on the right and it's an internal choice, you have to send. If the X is on the left, it's an internal choice, you do a receive on that. So we need to respect that. But having said that, you could put everything on the left and not even have a right at all. Okay? And And that's essentially what happens when you do use something called classical linear logic. Okay? And this one is called Intuitionistic linear logic, where we still make this distinction between a right and a left. And there's a couple of reasons to do that. One is that if you want to integrate this kind of thing into a functional language, and you want to have further exploration of the type system, it turns out to be simpler if it's more similar to what you already have. So the other path is not necessarily closed off, it just doesn't fit quite as nicely. Okay. Yeah, unfortunately there is no such construct in the language. So we don't have a freestanding sequential composition. Each construct, like sending something, has a continuation directly. And so that's just derived from the structure of the types. So we want to substantially reorganize the language to allow that. So that's currently not the case. But it doesn't seem implausible to do so, but the type structure doesn't suggest that. So this language is still developed completely by looking at the inference rules and reading off what the processes are. And there's no such process that takes P followed by Q sequentially. It's only the semicolon is always baked into a particular construct like sending, and then the semicolon is kind of associated with this particular operation. And there's no semicolon for a case. Yeah. Okay, other questions? Yeah?
Can you explain again the left arrow?
Okay. Okay, so if you have functional language, you write it like this. You would say merge of x, y. And it returns to you a value. Okay? Now in a concurrent language, you do not return a value. But what you do is you communicate along a channel with the outside world.
Oh.
And this is the channel.
So you're doing it right. You're doing it right to the stream.
Yeah, you're doing an output. Well, because it's a positive type, it's an output. If it were a negative type, you're doing a read from that stream. That's a little less usual in a functional language, but yeah. Okay, so normally you wouldn't, like I said, in a functional language it's completely redundant, but here you need to know that how to communicate along this channel. Everything's just a channel. Okay. So, we okay with this? Yeah?
So do you not use any case R type stuff anymore?
We don't use case R anymore. We just say case, and then the channel could be a channel on the right.
Okay, and in that case, could we send stuff to the left, like right to the left? Or like output to the left?
Yeah, we can send to a channel. But if this is an external choice, we would send to the left. Along a channel which is sitting on the left. Okay? We fine with this? Okay. So, okay, so let me rewrite the typing rules for just the construct we already have. But then something funky is going to happen. As soon as you have multiple assumptions, you get new constructs in the logic that you weren't allowed to have before, like implication. Right? We weren't allowed to have that because we had always one assumption. Now we no longer have one assumption, we get new connectives, and we have to look at the logic to see what these connectives actually mean, right? And they give you additional ways to communicate. So they give you new expressive power. This gives you some new expressive power only because you have multiple assumptions, but then new connectives gives you whole new different ways of communicating, okay? All right. So let me rewrite these rules. Okay. I'm unsure if these work or not, but let me try. Okay. So the NRE write rule for plus looks like this. So we have plus L A sub L, where L is drawn from some index set, okay? And On the left-hand side, previously we had a single thing. But now on the left-hand side, we have a whole context gamma. Okay. And what is a context gamma? Let me put it down here. Context gamma is either empty, we have nothing there, or we have a channel with its type. And we want all these channel names to be unique, so there's no confusion, right? All the channels that we're connected to have to have different names. Okay. All right. So if it's on the right, what's the operation? Well, we send along this channel, okay, one of the labels. So we say along X, send the label K, and continue as P. Okay? And what has to be satisfied for that is that one of the things we need to know is that K is in L, right? It has to be a valid label that we can send because it's one of the alternatives. And then the next thing we need to know is that in gamma, okay, X colon. Okay, so what is the type of the continuation here? It's A sub K, right? Because we send the label K. Okay, and we're executing the process P, the continuation P. Okay, does that rule make sense? Okay, so this is a finite number of choices between these labels in this label set along the channel X. We send one of those labels, okay, and then we continue communicating as A sub K, which is the branch that we picked out. Yeah?
What's the subscript on the A on the bottom?
That's AL. For every label here, there's potentially a different type A sub L. So for example, in our choice of bits, we could have B0 with continuation bits, B1 with continuation bits, or E with continuation alpha. So the continuation type is this type here. So I'll write a different table over here as a point of reference. Okay. So if you have a type, so this is the type. So if you have X colon internal choice between L, A sub L over some label set, okay, then what is the action you want to take? If it's on the right, that's what we care about. If it's on the left, you take the opposite action, right? So on the right, we send a label K from that label set along the network, okay? And then what is the continuation? Well, the continuation type is X will have type A sub K. So the weird thing here is that you're not used to from functional languages is that, you know, a variable of type int is always a variable of type int. But a channel of type, send one of these messages and continue as A sub L, you know, the channel will change its type because you're actually communicating along that. You're progressing along your protocol. And as soon as you send a message, you get, you know, the channel has a new type. Okay. And so that's what happens in that rule. Okay. Okay. And then we have to have the matching left rule. So in gamma, okay, or left rule. So we have a channel X of type internal choice L colon A sub L over a label set capital L. And over here on the right, we have some channel that we don't care about because we're not communicating along that, so nothing changes there. That's the usual thing we have in the left rules. And the process expression here is going to be a case on what we see on the channel X. And then there is a whole sequence of alternatives that look like L goes to, let's say, Q sub L for every label in that label set. And what does have to be the case for this to be well typed? For this to be well typed, we have to check for every L in the label set, we have to check that every branch is well typed. And every branch is going to be checked in gamma. X has type A sub L. And the right-hand side doesn't change. And the process in that case is just going to be Q sub L. Okay? All right, and then if those two communicate, what actually happens? So this process will send a label K, and then the channel X will go from having this type to having this type A sub K. This one will receive K, select the branch K from all of these. It must be one of them because we have checked they're all there, okay? And then continuous Q sub K, and X will have type A sub K. And we know that works because we have checked all the branches, okay? So with this formulation, that what I just walked you through is basically the proof of preservation. Okay. Proof of preservation doesn't mean that all the variables continue to have the same type, but it means that if you plug two processes together across this interface, this channel X, okay, then after they communicate, they will still agree on the type of X. This one will be A sub K, this one will be A sub K. Okay, so we should get back to the other rules. And maybe I should have done this first, okay, but the cut looks like this. So we have a context gamma, okay, let's put it this way. We have a context gamma 1 and we have a process P, which offers along channel X of type A. And then we have a client which uses the channel X of type A to provide Z of type C. And then after the cut, what you get down here is gamma 1 together with gamma 2. Okay? And then you get the parallel composition of P and Q. So I would be tempted to write P in parallel with Q. Okay, but that actually I can't write because I need to know that P and Q communicate along this channel X. So I need to put X into the picture. So one thing I could write is something like this. P and Q communicating along X. It's very hard to write this in concrete syntax, okay? So the way we do this is operationally we spawn a new process P which offers along X, and then we continue as Q. So there's actually a sequential aspect to this in the syntax, okay? When we get to this process here, we spawn a new process P, that'll provide X, and then we continue as Q. And Q will be mentioned in X, so we'll actually use that. So Q will be the client of the process that it spawns. So you spawn a process P, and you will be the client of it, and the way you can communicate with it is along this channel X, okay? And then in the pi calculus, if you're familiar with that, this would be written as a private channel X that has P and Q in parallel. Okay, so that would be the notation in the pi calculus. But in concrete syntax and writing programs, this is not very useful, so we're writing it like this. Okay. Okay, makes sense? Questions? Yeah?
Does that mean actually P and Q are executing at the same time, except it's just a syntax that makes them sequential?
No, not really. So what happens is that in your program, as you execute it, you go through these things. You go like through here. You do some operations. And then in your syntax, you hit this point in time. And when you hit this program, you actually spawn a fresh process. You do a spawn. After you spawn, then they execute in parallel. But before you spawn, you just have a thing that says spawn a new process P. Okay. And that you have to spawn it before you can continue. But after you've spawned it, then you run in parallel. So there is some sequentiality to this operation because we say exactly what to do. We send a message, we receive a message, we do a case, then we spawn a new process and continue and so on. That's why I think the semicolon is actually okay. See, in the pi calculus, there's no distinction there. There's no actual explicit operation that says we spawn a fresh process. You just have P in parallel with Q, and it somehow magically happens. But not here. There's an explicit operation to spawn a new process. Okay, and we also need identity. Okay. Now identity turns out to be easy to describe but very hard to implement actually. So identity in linear, well, as before, it looks like this. A proves A, right? That was all. And so we do the same thing. We have y colon A in our context, and we have x colon A over here. And the forwarding, which just was a double arrow before, now we have to say x is implemented by y. Okay? So this is sort of like equating these two channels, or it's forwarding between them. And we're saying now from now on x is implemented as by y. And this process then terminates, and these two channels are actually connected with each other. Okay? Yeah, so this is an operation that the pi calculus does not have. Okay? If you look at how to implement things, pretty much everything I showed you here is completely straightforward to implement. And we have done it multiple times, except for this operation. Okay, forwarding is a really tricky thing. Now, the theory tells you, the logic tells you, it must be there. Okay, there has to be such a thing. And when you start writing programs, you see it comes up all over the place. Okay, yeah. Yeah. Yeah, that's an excellent. So there is actually a bijection when the program runs. At every point in time, every process that runs has exactly one channel along which it provides a service. Moreover, for every channel that exists, there is a process that provides it. So in some sense, you could say, well, the process is identified with the channel along which it offers a service. Okay, and we like to think of it this way. What makes it a little bit tricky sometimes is this operation, okay? Because there's a process that provides y, and this is its only client, and now suddenly its only client becomes x. So there's something weird going on if you try to take this particular point of view with the forwarding operation. So you have to slightly modify. You don't always offer along the same channel, or you have to contour to make that sure that happens. But yeah, we can identify channels with the process that provides them. Okay, and because of the way that the logic is constructed, what we have, whenever the processes run, they describe some kind of a tree. Okay? So if we have a context gamma, so we have gamma, which is x1 colon a1, xn colon an, and then we have p, which does that. Right? The picture you should have in mind that there's p here, and it provides z to the outside world, which has type A, and it uses x1 through xn over here. And these again are provided by some processes Q1 through Qn, and they may use other channels. And eventually it bottoms out. It stops at the situation when there's nothing in the context, when the context is empty, because then we get to these processes here that don't depend on anything else. And the relation is always that this process P here, if you say this process P is a client of of these processes and provides this one. Okay. So Q1 provides X1 is a client of it.
Would the intuition provide this as linear? Like, why is the output P couldn't be used by multiple other processes?
Well, you see the way the cut rule works here, okay, is because we're working in linear logic, okay, X occurs in exactly one place, so we have exactly one client. And moreover, we have to be very careful here in the rule, and I glossed over this pretty quickly, but these are all the channels that this process uses. When it spawns a new one, it passes all the processes, all the channels in gamma 1 over here to P to use, and it no longer has them in its continuation. It takes only the remaining channels and the new one that it just spawned, right? So that guarantees that's very strong invariant in the system that any process always offers exactly one channel. It might be a client for multiple one, including 0. Okay? And that's critical when you try to prove progress and preservation of these things. So your processes so far always form a tree. Now that being said, it's possible, and we have done this, to generalize this picture so that it doesn't have to be necessarily linear. In that possibility, a variable here that's not linear could be reused and could have multiple clients. And that would mean that this picture actually doesn't apply anymore. But in order to do that, you have to generalize away from linear logic, and then you have to worry about what is the meaning of having multiple clients. Okay, how do we actually think of that? Okay. So if you want to know the answer to that, roughly what happens is that, well, we need to do some programming, but if P has multiple clients, okay, then if it's a positive type and you send a message, it's like a multicast. Each of the clients will receive that message. Okay, so it gets copied essentially to all the clients. If it's a negative type, so it actually receives the message, okay, so that's like an external choice. The first one was an internal choice where you send a label, all your clients will receive it. If it's an external choice, then what happens when you receive a message, you spawn a new process, a copy of yourself, to serve that request, okay, and the other clients will still see the old process, okay. So that's how it works out if you allow potentially multiple clients. But it's actually quite tricky, and there's a lot more to be said about this, just as a hint what it would look like. So we're not in this, we're still in linear logic, so everything is a tree, and things are quite simple. Any more questions? Okay, so then what I will do next time is we will explore programming in this logic, and we will explore the additional connectives that we have available now that we have multiple assumptions. We can define other things like a form of implication, a new form of conjunction, and what they will correspond to essentially is that you can pass channels along channels. Okay, so you can send and receive channels. You can dynamically change the communication structure of all these processes. Because, for example, Q1 could take this channel and pass it over here, and then P could pass it over here. So you can rearrange the way that your tree looks at any point in time. And so that gives you a whole new way of writing applications, data structures, and things like that. So, so I think, given how far I've gotten, what I will do in the last lecture then tomorrow is I will briefly complete the picture in terms of the connectives. So we have some new connectives, new ways to express, and then we'll spend the rest of the time writing some code in this now fully expressive language. Yeah?
In the singleton version,
Yeah.
we had the get elimination.
Mm-hmm.
And if I understand everything correctly, that means that we can do away with the parallel composition in theory? Because we can eliminate fetch data, but also replace it by other things.
Yeah.
Yeah. Do we have the same thing here when it's no longer a single?
Yeah, so as long as you don't have these recursive types, you still have cut elimination. And so any program that doesn't use any of these circular types, even though it may have a very complicated dynamically changing structure, will terminate and be cut free at the end. But there aren't very many programs like that because most programming goes over recursive types. And then again, you can ask the same questions. Do we have least and greatest fixed points? And we can check that the programs obey some conditions. But that's kind of still ongoing research. Other questions? Okay, we'll see you guys tomorrow.